All right, so today we're going to talk about trigonometry. And this is a new subject for us, and it's about ratios and right triangles. When we're used to similar triangles, we know triangles that have two angles the same, that match, and two triangles means that the triangles are similar. So the ratios of their sides are similar. So in this case, because I have a 90-degree angle and angle A are the same as the 90-degree angle and angle D, angle means angle. It means that triangle ABC is similar to triangle DEF. It means the ratios of these two triangles are equal, okay? So if I call this O, A, and H, and I call this O1, H1, A1, we're going to know that O over H on this triangle is the same as O1 over H1 on the other triangle. All right? Or O1 over A1 would equal O over A. And since 90-degree triangles always have one 90-degree angle, we know this is a repeatable thing, okay? But the first thing we got to do is agree on a pattern to identify triangles. So when we look at a right triangle, the one thing we know is there are two legs and the hypotenuse. So we can always quickly identify the hypotenuse. It is always across from the 90. If I use the abbreviation HYP, that's the hypotenuse. Then what we want to do is select the angle. If I use angle X and I stand on angle X, my little guy, all right, we have to identify the legs and give them a name so we can talk about triangles. The leg across is what we call the opposite leg. So I'll call it OPP. All right? Now we've identified the hypotenuse, the opposite, and that leaves the adjacent leg, ADJ. Okay? This way we can talk about the angles in the same way every time. But there's something to realize. If I have that set up based on angle X, if I stand my little guy on angle Z, the hypotenuse doesn't change. Hypotenuse is still across from the 90-degree angle. But the opposite leg does change. It's still the one across. And that leaves the adjacent here. The adjacent side touches the angle. The adjacent side touches the angle. The opposite side does not on both triangles. And it changes based on the angle we're looking at. All right, and that's the key to that trigonometry, is we have to be able to identify the opposite, the adjacent, and the hypotenuse every time, so we can have a discussion about them. Recall, it's all about similar triangles. So if I call this the degree angle, we have the hypotenuse here and here. From A across, we have the opposite. From D across, we have the opposite. And we have the adjacent on the bottom and the adjacent on the bottom. So when we look at angle A and D, we have these sides. And what this allows us to do is to look at the ratios of these sides. In the old days, we would do this with tables. We'd have the degrees listed on the side, and we have something we call sine, cosine, and tangent. And the ratio is actually a value that they divide out, and they recorded it by tenth of degrees what that ratio would be. By doing this, we could look this up. We no longer have to do this. Your calculators have sine, cosine, and tangent on them, and that's what we'll use. But again, this is the ratio for all these rectangles of a certain angle. So we're going to use common ratios of sine of A, cosine of A, and tangent of A, which you saw the abbreviation is sine, cosine, and tangent. So when we look at a right triangle, and again, and we use A, we're going to have the opposite here this time, the adjacent, and the hypotenuse. And we're going to set up ratios of these triangles. Now we'll talk about what those ratios are here in a little bit. But first I want to make sure we can do the opposite, hypotenuse, and adjacent. And if you're good at it, you can fast forward through this section. But I'm just going to sit here and identify in these four triangles the opposite, the adjacent, and the hypotenuse based on the angle that's marked A. So, and again, I'm not going to draw the arrows here. So again, I'm going to start with the upper left here. The hypotenuse is here, across from the 90 again. So next I'll identify the opposite, which is across from the angle. And that leaves the adjacent, which touches the angle, and it's a leg. Now I'm going to go to the second one. Again, if you pause me, you can take your guesses. The hypotenuse is across from the 90. The opposite is across from the angle, and the adjacent touches the angle. And finally, if I look here, the hypotenuse is across, the angle is opposite, and the adjacent. Last one. Hypotenuse is across from the 90, the opposite, the adjacent. This is how we identify the triangles. If I come back here, we identify sine as the opposite leg over the hypotenuse for the ratio. We identify the cosine, it's this over this for sine. We identify cosine as the adjacent over hypotenuse. And it always has to reference an angle. You always have to have cosine of an angle. It has to have some measurement. And finally, tangent of A is simply the opposite over the adjacent. Now this is a lot to remember. So we came up with a little phrase to help us remember it. Sakatoa. Where the S stands for sine, opposite over hypotenuse. C stands for cosine, adjacent over hypotenuse. T stands for tangent, opposite over adjacent. And every time we want to do a ratio for trig, for trigonometry, we're going to use Sakatoa. And we're going to identify ratios of right triangles. And because the angles are always the same, again, there's tables of these values. And your calculators have these stored, so you're at your fingertips to grab. And the similar triangles are right here, and this is the ratio. And this will allow us to find missing legs and missing angles eventually. But first we have to be excessively good at finding the trigonometric ratio. So find the value of the trigonometric ratio of each of these. And again, I'm just going to run 1 through 6. Remember, first thing, Sakatoa. All right. It tells us that it wants a tangent of A, and they want to know what that ratio is. So the question is, what does tangent of A equal? First thing we got to do is mark A. We know angle A is there. The hypotenuse is across, so that's HYP. The opposite is across here, that's 24, and the adjacent is here. All right. We know that tangent is opposite over adjacent. So the opposite leg is 24, the adjacent is 32. If we wanted a decimal, we could take 24 divided by 32, okay, and get a decimal point. Or what I'm going to do here is we're going to reduce this to a different ratio. It's 24 and 32 both have 8 as the greatest common factor. So we can reduce it by 8, and I get 3/4. Or on the tables, it would say 0.7500. That is the answer for the first one. I'm going to go through and do the next 5, all right? If you want to try to do them ahead of me. The next one is the tangent of C. The hypotenuse, the opposite, the adjacent. Again, tangent is opposite over adjacent, so it's 16 over 12. Both divisible by 4. So tangent of C equals 4/3. Next one says sine of Z. Again, we're going to identify the legs, hypotenuse, opposite, and adjacent. Again, these trig ratios only work in 90-degree triangles. You must have a 90-degree triangle to use these. Sine of z. So sine is opposite over hypotenuse. The opposite is 6. The hypotenuse is 10. 6/10 is the same as 3/5 reduced. All right. I'm going to write the answers for the last three here. So if you want to try those three on the video, I'm going to just put the answers up on the board. Sine of z is 4/5 for number 4. Sine of c is 21/29 for number 5. And cosine of x, there's number 6, which is adjacent hypotenuse, using x is also 40/50, which reduces to 4/5. These are trigonometric ratios. Once you can do the trigonometric ratios, we can find missing sides and missing angles later. It's a powerful tool we use in the world.